Vector search. It's a really interesting technology. Arguably, it's the first really big thing to happen in search for almost a decade now. But as with anything that gets a lot of hype in the software industry, I think you have to ask a few hard, practical questions about it. Are there any real business use cases for this? Is it solving real world problems? Is it solving money problems? Is it going to solve my customers' problems? And if you've got good answers to those kinds of questions, then is it really ready for production? And what do I need to know to make it work for my business? Well, my guests today are a couple of people who have some good answers to all those questions, and I get to grill them for you. I'm joined by Matan Kollenscher of MyPart. He's using vector database search to overhaul the way songs are found for film and television. I'll give you an example. I think Quentin Tarantino is a genius at dropping the perfect song into a film just at the right time to set the mood for a scene. If you're a fan of his films, you'll know this. He just drops bangers. And there are a lot of TV and ad companies searching through record collections manually, trying to replicate some of that magic. But it's slow and it's expensive. So Matan's going to take us through how he's been turning that right song at the right time problem into a machine learning solution that takes microseconds. And that's actually really big business. And then we have Itamar Syn-Hershko to take us through the practicalities. If you've got a vector search problem, how do you implement it at scale? What do you need to know? Itamar's going to take us through his approach using AWS OpenSearch and some tools from around its ecosystem. So I'm Kris Jenkins. I'll be your host for this, the first in a series of webinars from BigData Boutique. Let's get started. Matan Kollenscher, how you doing?
I'm good, thank you. Pleasure seeing you again, Kris.
It's glad you're here. So you've managed to combine two of my favorite things in the world. You've got technology, especially in the exciting world of machine learning, and music. You've got this resplendent collection of records behind you. So what is it you actually do with these two fine things?
So MyPart is basically the only AI-powered song search out there. Note that we're saying song rather than music, because music recommendation is often mistaken as something that only relates to the sounds. When you talk about music recommendation, people think about genres and maybe moods. When we talk about songs, we mean every single dimension there is in a piece of music or a song, which includes lyrics, musical composition, which is chords and melodies and rhythmical elements, etc., and production and sound. So there are basically three dimensions that you need to conduct independent search in order to find something super accurate and relevant.
Right. So is this like, if I were looking to put a playlist in my car, I'd maybe focus around 60s rock, let's say. But if I were a DJ, then it's not just about being in the same era. I have to find a song that fits a certain feel, a certain tempo. Maybe yes. I want to connect the lyrics together.
That makes perfect sense. Those are some consumer challenges or use cases that make perfect sense. At MyPart, we started with more professional use cases, the likes of I'm the director of a film or a TV show, and I'm looking for the right song to place in this scene. Or I am the director of an ad, and I'm looking for the right piece of music to put as part of my advertisement, which will speak the language of the brand. Those things tend to be far more specific, and you need to be really accurate about they call it placements. So in many cases, you can start either by defining with words what you're looking for, which is kind of what you did. So I want it to be from this decade, this type of genre, up-tempo, female, etc., etc. Usually, it's not enough because there are so many female up-tempo pop songs.
True.
So you end up having to go through thousands of potential placements, and it just falls short. It's much cooler if you're able to also look for things from the realms of lyrics and music and say, okay, I'm looking for a love song, but one that's not nostalgic, because this is happening now. So scratch nostalgia off from all the options you're giving me. There's a tint of cynicism here in this scene, and she's not so sure about him. So can you give me something with a tint of cynicism? It's not going to describe the scene. It's just going to be a bit cheeky. And I want it in a minor key because I want it to be a bit mellow and melancholic. That's where it gets more interesting. All of that is one way to search, when you know how to articulate what you're looking for.
This sounds like the kind of problem that can only be solved by getting someone with an encyclopedic knowledge of music and getting them to dig through their record collection.
I love that comment. So I would agree. And if you go to music companies and ask how they solve this problem today, that is the real answer. They have someone, usually 40, 50, 60 years old, with an encyclopedic knowledge of everything that they have. And everyone in the organization fears of the day where they'll, go to the competitor or disappear for other reasons.
Yeah.
In addition, I would say that even those geniuses who live music, when they are tasked with something a bit more complex than your usual requests. Let's go back to the example we were giving. So I want a song that is about love, but not in a nostalgic way. And I want it to be pop, but like towards rock. And I want it to be in a major key. And if possible, I would like there to be like 2 or 3 really repetitive hooks, melody lines, because I need the audience to remember those hooks, and I'm going to maybe use them later. No one's encyclopedic knowledge is able to just pull that up.
No.
So even these people end up spending weeks, if not more, on brainstorming. And in many cases, it's a fluke where they end up actually getting something that's a perfect fit. There's a recent case that I think serves as an interesting example, where a Kate Bush song from 1986, because of its placement in Stranger Things, the Netflix series, became the only female song that has surpassed 1 billion streams on Spotify from the 80s. The
Wow.
only one. And if you read about how the supervisor who found that song found it, her name is Nora Felder, you'll see exactly the process that we're talking about here. It's the whole process of finding and licensing the song, brace yourself, took 2 years.
2 years.
2 years from the moment that she was tasked to find something fitting for that scene or few scenes until it actually got finally approved and put into the, into Stranger Things. That's
it
how
worked, right? It's like 2 years well spent, but gee.
2 years well spent, and some people say it's the placement of a decade. But what if? And that's what tickles us. What if that could be reproduced on a more common basis?
Yeah. I'm trying to translate this into my knowledge of machine learning stuff. And I can see how, from a certain point of view, like a vector database is like creating a map of the space. And I can see how certain clusters of songs would sit in certain clusters on that map. And so your client comes along and says, I want to be on that space in the map. What's roughly in this space? What I can't see, and what I need you to explain to me, is how on earth do you take a song and turn it into a list of numbers, which makes up a vector map?
So I won't tell you how to do it.
You're not going to give me your trade secrets.
Exactly. But
you can give me the shape of it, right?
I will happily share some thoughts and insight about how we got there and why vector search is indeed part of the solution, and what other types of machine learning and AI sprinkles you can put on top. So in composition, for example, there's a whole field called functional harmony, which is basically a theory that talks about which chord to put after each chord. What makes sense, what makes less sense, what progression is gonna incur certain feelings or expectations from the listener, and what will do something else. So each of these things, if you formalize it, you can then start thinking, okay, so if I'm trying to solve that problem, how can I have a computer understand that? So if it's chord progressions, then I need something to extract the chords. And I need to know what the length of them was and how they work one after the other. Where does a phrase start? Where does it end? And then it goes into what types of chords. So is it a 3-note chord, a 4-note chord, a 5-note chord? I mean, things that guitarists and pianists, they just know because this is what we do.
Yeah.
Each of these things has a meaning when you compose and when you perform. The same goes with lyrics. So you can talk about what the song is about, what's the narrative, what's the storyline. Of course, you can formalize that. To what extent is this a love song? To what extent is this cynical? To what extent does it revolve with me or you or someone?
So I'm chewing through the lyrics and getting the character perspective, that sort of thing.
Exactly. So you want to understand who's telling the story, what's the narrative, what is the main agenda, what message is it trying to convey, and all of that is in the realm of theme and mood and context, etc. There's so much research on this topic outside of lyrics, but I haven't seen, especially by when I started MyPart, but even to this day, I've seen very few who have applied semantic analysis and theme and mood analysis to lyrics, especially not in a commercial way. It's just it hasn't been done. Try searching Google for love songs that are not about relationship. It doesn't work like that. You need someone to have compiled a playlist.
So can you do things like navigate this vector space by saying, okay, give me someone like Kanye West in that style of music, but I want their way of writing to be more Bob Dylan-ish. Exactly. Who's the most Bob Dylan-ish hip-hop artist?
So that smile that you have on your face is where this becomes really fun. Because that's the creativity. You tell yourself, ooh, wow, this is really cool. But you know what would be even more cool? Because I want to listen to it, or because I need something like that. So back to the example we were giving. So Kanye, Black Skinhead, I can't use that song because the lyrics are too aggressive, too religious, too whatever it is that they are. So yeah, just that minus these things plus more of that. That's where creativity comes in, and that's a beautiful thing to be able to do. And we can do that. We can pull that off.
So, for those days that you want Nirvana, but cheerful.
Exactly. By the way, think about it, and then just try to do that math in your head. It's really difficult.
Yeah.
But in vector space, it's doable, and you can literally tell it. You see this? Give me a bit more rock, a bit more grunge, but with positive lyrics, something empowering. That's what I'm looking for.
Yeah.
So let's dive one step deeper into your question in the context of so what do you do technically here? So part of the solution is very natural to the vector space. You're basically looking for similarity in several vectors, each of them representing part of one of the dimensions of the world. So, for example, in our case, music is one vector, writing style is a second vector. What is the song talking about is a third one, and how does it sound like is a fourth one. Each of these is extremely intricate and detailed. You extracted all of those pieces of information that you're able to extract from the lyrics and the audio. And then in vector space, you can do exactly what we said and say, okay, so something that sounds like this with a composition like that and lyrics that talk about this. That's literally similarity search or the part of song search, which you can do with another song or a group of songs as seeds. The other thing you want to do, and I think you also refer to that, is sometimes you want to draw a line around the vector in certain places. So you want to say you see this in 1,000 dimensions. So picture that I'm drawing a line in each dimension, and I'm saying, you see this polygon, this is pop. This is where I draw the line. If you're beneath it, you're rock, and if you're to the right, and again, all of these directional terms, you have to multiply them by the amount of dimensions. But in general, you want to draw those lines. So that is more, if you think about it, more of a classification problem. Yeah. You want to draw the line somewhere. You want to train the model to know in each of these realms where to draw the line between things that we have a name for. Usually that type of search is less accurate, but you're not using it for its accuracy. You're using it because you want to filter either outside or inside of your query only things that are more likely to make sense for your query.
That leads into optimization. Okay, so you've got this engine of music, which is very cool. And I know it's been in production for a while, but you've recently done a big overhaul of it, right? Tell me about that.
So the use cases that we talked about, TV, film, ads, and A&Rs looking for songs for their artists, are all B2B. You're working with a business. They have projects that they're working on. Usually these projects are, like we said in the Stranger Things example, they're going to take a while. To solve or to support those use cases, time is not necessarily or query time is not necessarily the most important thing. You can start a search, and if it comes back in 5 minutes and it's amazing, then you've saved 2 weeks. Who cares?
Yeah.
Usually you also have a couple of projects or you have a couple of songs that you're considering. So by the time you're done finishing your third or fourth query, if the first one returns and you can start working, that's okay.
Yeah.
What we've seen is that the bigger the catalogs have become that we're searching, the longer the queries take. So the analysis is one thing, but the query is somewhat linear or almost linear to the size of the catalog. And when we started reaching hundreds of thousands of songs that you search through, we wanted to do better.
Yep, that makes sense.
And that was an interesting opportunity for us because we started saying, wait a second, we have this crazy engine that can answer questions for the most talented professionals out there. What if we can give, Kris, for just his pleasure and playlisting and DJing, all of those use cases that you started with, what if we could give you access to this? And what if instead of having just, Universal Music's catalog and Warner's catalog and Hypnosis songs, what if it had every single song that counts? What if it had every single song with more than 1,000 spins on Spotify? Wouldn't that be cool?
Yeah, totally.
If we were to do that for the consumer, tens of seconds or minutes of query time is irrelevant.
Yeah, no
You're
consumer's
not
going to
going to
wait
go
around
grab
that
it.
long.
Exactly. We all have an attention span of a mosquito by now.
So you've got a few 100,000 songs and it's taking minutes. You need to get to the point where you can do 30 million songs sub-second.
Right. And that is, after a lot of research, what brought us to AWS's OpenSearch.
Right. So take me through that. What brought you to the conclusion that OpenSearch was the right fit?
So we were looking for something that ticks all these boxes, and we were coming out blank. And we basically developed our own solution. We started developing our own solution to do that in a way that is as effective but faster. And then we had some brainstorming sessions with cloud providers of ours. One of them, luckily, was the AWS team. And one of them, after listening to what we need and how we have implemented it, and the type of information that we need in the search so that it actually works, had an idea. And they said, I think OpenSearch ticks all those boxes. So let's try.
And how's it working out?
It's been amazing. Basically, I would say within 3 months, about 3 or 4 weeks of them of work net. The rest is designing and defining and architectural discussions, etc., and some learning that had to take place for us to utilize a new interface or a new infrastructure. We were able to bring down that query time that took minutes for the use cases where it made sense into 200 milliseconds.
Nice.
Without losing granularity. All of our data is there. All of the coefficients that are basically knowledge that we transfer from our research into what is more and less meaningful in every vector. All of that goes into play, and with very, very subtle changes in research of algorithmic subtleties, we were able to mimic results, the quality of results that we were getting with our own code, our own implementation. And we have a good reason to think that we'll be able to surpass the accuracy and precision that we were achieving by further fine-tuning what we know into OpenSearch capabilities.
Nice. And you think that will scale to growing the catalog up from hundreds of thousands to millions?
So suddenly the limitation, which was so daunting, seemingly at least, is not there. So our dreams of applying this to the consumer world, where you don't just work with one catalog, is a real option. And we're super excited about that. And I can't tell you of all the use cases that we have under our sleeve, but hopefully you'd be hearing about them quite soon.
Cool. I want private access. I had some people around for dinner last night, and I couldn't think what to put on that everybody would like. So maybe one day you can help me with that.
Definitely.
For now, I think we should go and dive into the gory details with Itamar. So, Matan, thank you very much for talking to me.
My pleasure, Kris.
Okay, I confess I could get distracted at this point, start digging through my favorite playlists for interesting questions, but I'm going to stay focused. We need to talk about how you use this tech on your own problems and how you get it into production at scale. So let's have a word with Itamar Syn-Hershko. Itamar, you're Matan's OpenSearch vector space guru. I know you're going to give us all the gory details about all this, but before we get into that, I think you should give us your credentials. What makes you a guru about vector search?
So it's me and my team. Essentially, I've been using Elasticsearch, which OpenSearch builds on, for over 13, maybe 14 years now, including contributions to the code base and search algorithms and search engines in general. Now I lead a company called BigData Boutique. I'm the CTO and founder of the company, and we have world-class experts working for us on big data projects, search projects, information retrieval, and the intersection with ML, machine learning now. We've been doing Elasticsearch and OpenSearch for many, many years now. And recently, we also started doing a lot of search ML and vector search projects. So we've been doing that for a while. And that's how we got to Matan and MyPart, the MyPart team, and helped them do this amazing project.
Nice. Okay. Now you're going to help me out with this. I'm building up this mental model where the trick is you've got this data set, you could be searching in a better way, in a more interesting, richer way. The trick is to convert that data into this vector space map somehow. And then you can start getting the computer to query it in fun ways. So let's start there. How do you do this translation from whatever my data is into vectors in some vector space?
Yeah, so that's actually a lot of data science work, and there's a lot of knowledge and a lot of possibilities over there. I think it makes sense for us in this scope today to actually talk very broadly about that. So essentially, you are going to run various types of models depending on your use case, right? Depending on what you're trying to do. So you would have a video, and you would pass it through some sort of a transformer, some sort of a model that takes that video and produces a vector. Now, that vector, you need to do some feature engineering. What exactly you want to extract from it? Are you going to extract, is it a fast scene, slow scene? Are you going to extract the length? Are you going to extract the, colors that you have in it? So it really depends on what you want. How do you define similarity between videos in this case? In MyPart's part, right, no pun intended, the song search actually represents quite a few things, right? It could be the melody, it could be the lyrics. So again, how do you create a vector, maybe more than one vector, to make the song representable by some sort of a binary model that then we can search on. So that those transformers are going to be, or models are going to be very, very different depending on your exact use case. And then there's a lot of data science work that's going to go into that to make sure that, as you would imagine, there is some sort of a training set and then some test set, and then you continuously improve that model that it makes sense and search actually works for your use case and satisfying the KPIs that you have.
Yeah. But some of this, right, these days, you can kind of get off the shelf, those embedding models that translate. Absolutely. And sometimes you have to do it yourself. Yep. Are there particular cases where it's an obvious, this has already been done for you?
You have those, new LLMs that everyone is talking about, and Hugging Face, and a lot of kind of libraries of, if we talk about text for a second, a lot of libraries that allow you to take those texts and create some sort of a vector of an embedding. And that's today very, very common and easy to find. There are plenty of models that you can just Google and find. It really, again, like I said, it really depends on your use case because you would need to find the right transformer, the right model to do what you need to do. But first you need to define what you want to do. I assume for semantic search, there are actually more approachable models and tools that you can use to create those vectors.
Take me through the navigation of that space. How do we do it?
Right. So if you wanted to start with vector search, you're going to need 4 things, essentially. So vector embeddings, which is essentially what we just discussed, right? You take data and you transform that into a vector. a vector embedding is what we often call that. And this is a binary representation of the things you would want to capture, right? Like I said, everyone would maybe capture different things based on the vertical and what they're actually trying to do there. So that's the vector embeddings. Once you have a vector embeddings, you need to settle on a way to find those vectors. So that would be the distance metric, right? So you have two vectors. Let's imagine, two-dimensional space, 1 point here, 1 point there. Are they similar or are they not? Or what is the distance between them? Because if I'm going to have another vector, is it closer to this vector or is it not? Right? So there are distance metrics that you basically need to figure it out. Again, it's basic math. It's linear algebra. There are a couple of distance metrics. We can talk about that in a second. But essentially, those distance metrics, you need to settle on that because that will essentially dictate what is a similar vector and how similar it is to your search vector. Right. And then once you have that, you need to also decide on how you're going to search on that. There's a lot of trade-off on, performance and required hardware like memory, for example, and accuracy and even ingestion speeds, right? It's because if your vector space is not static, it actually accepts more data all the time, then maybe ingestion time, how fast and how accurate new vectors are going to be added to that vector space.
Oh, yeah.
So that method also makes a lot of sense, or it's something that you want to get right, or at least test for. And then, like you mentioned, we need the database software to basically take all of those and make it approachable to you using some sort of an API. And for my part, we chose OpenSearch, and we used OpenSearch to basically tie all of those together.
Okay. I've asked Matan this, but I think I'm going to get your side too. Of all the options, why OpenSearch?
With OpenSearch, we actually have a lot of experience with. Again, personally, I've been doing this for over 13 years now. Elasticsearch, now OpenSearch, and we've been doing a lot of projects, the team and I, in the last few years. So it was very much of a natural choice. And OpenSearch actually put a lot of effort in the last 1, 2, 3 years, basically since they created that project, and they put a lot of effort in making vector search efficient and usable. So you get a very easy to understand API, a very easy to use API, and some flexibility around how you do things there. So that's on the vector search part. But then you can also use filters. You can use full text search, just good old full text search, just terms-based search, and geospatial search, and other types of search, because OpenSearch is a search engine first and foremost.
Yeah.
And then it also introduced this vector search, which is not a whole new thing that you need to use only that, but it works in conjunction with everything else over there.
Right. Yeah, because I've definitely seen some people entering the vector search space and they just do vector search. Being able to mix and match would be nice, right?
Yeah, again, those kind of, what other types of search you can add is a topic, right? I mean, everyone is interested in having more than just vector search. I think OpenSearch does a lot of things right, including how do you manage it in scale, the managed offering, specifically in this case by AWS, and plenty of other features like that make it pretty much of a natural choice. So we were able to do something very efficient, and both in terms of performance and relevance, that just made it a no-brainer. I mean, we just bet on the right horse, and the horse that has been there for a while. Not old, but has been there for a while.
Right. Yeah, the established horse.
Established horse.
Yeah. Okay, I think we should dig in a bit deeper. You give me some computer science stuff here, right? So, navigating this vector space, I don't want to go too far into this, but give me something about how we calculate all this vector stuff so I know where we are.
Absolutely. So, vector embeddings, check. You should have vector embeddings already, whether someone gave it to you or you computed it on your own or even build a model to do that. Then once you have the vector embeddings, you can decide on the distance metric. Again, once you create those vector embeddings, you've pretty much settled on the distance metric already, just because how those vector embeddings are usually generated. You create them with a specific length, normalized, not normalized, and then you get to some sort of a distance metric that would make sense. Are you going to use cosine similarity, meaning you only care about the angle between the vectors, or is the length interesting as well? So those are pretty much dictated by the way that you're going to build the vectors. Right. And then you need to decide on how are you going to look for those vectors. Now, looking for vectors or vector search is essentially something that's called KNN. K nearest neighbors. K being the variable, right? So if you want the top 3 vectors that look the same or similar to the vector that you're running as a query, then you're going to basically say KNN, K being 3, and you're going to run KNN. Now, here is a little bit of a confusing piece. When people say KNN, what they should mean is KNN as in exact KNN, meaning I want the K most similar vectors like my vector, given the distance metric and etc. But KNN is used interchangeably a lot with ANN, meaning an approximate KNN, approximate nearest neighbors. And that's an important distinction, because KNN will give you vectors that are absolutely similar given the distance metric and etc. Or the distance between them, and it will be accurate. But it's a brute force approach. Basically, we're going to iterate across all vectors in the space, right? Maybe we applied some pre-filtering before that, hopefully, but we will iterate through the entire vector space and calculate that distance metric, sort by it, and that will be your KNN. Just take the K first ones from that sorting. The problem with that is it's very computational expensive. It's very computationally expensive, and essentially it's going to be very, very slow, especially with large data sets. So it's not scalable.
Right. So this relates to what Matan was saying, like they had this problem that as their data set grew, their query time grew proportionally.
Absolutely.
Yeah.
It's basically linear at the number of vectors. So each computation of the distance metric is essentially microseconds or nanoseconds to compute. But as you grow, and we can even parallelize that a little bit, right? Because of how OpenSearch works, it's a distributed search server, search engine. But as your numbers grow and grow exponentially, it's going to be you cannot scale that in terms of latency, and that's where ANN or the approximate KNN lookups are going to come in, and that's basically what's our recommendation for anyone doing vector search. Go with ANN, right? And again, KNN, ANN are going to sometimes be used interchangeably because of that. Your first go-to should be ANN, to be honest. Although in small data sets, you'll probably be okay with KNN, and that will maybe simplify some things. So ANN is essentially it's the same concept, except we apply, and that's a lot of data science, and I'm not a data scientist, but we're going to apply a lot of pre-training sometimes, but we're going to apply a lot of algorithms and a lot of optimizations to make sure that we only look at a subset of the vectors to begin with, right? You can think of it as a huge space, think two-dimensional space, and then you kind of group you group a lot of vectors in groups. And then when you have a vector, one of the methods, for example, will look at the centroid for each of the group. So the center of, all the vectors in each group.
So this is like if I'm looking for blues songs, you find me the most bluesy blues songs of all the blues songs.
Yes, except again, it's all about the vector space that you have and how close those vectors are to each other, and how much loss or what is your error rate that you're going to have. But that's ANN, that's approximate, and so you're trade-offing accuracy for speed, and you'll have to measure that. You'd have to look at your data set and understand how it's going to be prone to those kinds of errors and by how much. So that's something that's important to understand. But to be honest, vector search at scale has to do that in some way. And again, there are a few optimization processes and quite a few optimization algorithms and methods that you can take. And you absolutely need to try, right, which one is right for you. Again, using data science methods with training set and test sets. Right. So
there is an iterative process going on to get the right results, the right pipeline.
Absolutely. Search has always been a data science, kind of practice, right? You always needed to have some data scientist in the team to look at to measure relevance, to see whether it's improving, what makes it to improve, what makes it regress. But yeah, in vector search, it becomes ever more important.
Right. Okay, so do you want to dive into some of the technical details of how you optimize an approximate nearest neighbor search?
Yeah, so again, OpenSearch is actually a search engine. In its core, it's Elasticsearch. It's Elasticsearch and a search engine that has been built like over 10 years ago. And then, it evolved and the core is very, very stable. And then Amazon essentially forked Elasticsearch a couple of years back and renamed it OpenSearch. And now it's fully open source, Apache licensed. And then it essentially keeps the same characteristics of Elasticsearch, except OpenSearch did a significant amount of work towards a vector search space, right? So they now allow you to do vector search in several ways that make it much faster, much more efficient. And what they did is actually they implemented two engines in addition to the one that has already been baked in. So you have Elasticsearch and OpenSearch, which are based on Lucene, the famous text search library. And Lucene version 9 added the ability to do vector search, not only text search or numeric search.
Okay.
And so they have a built-in engine for that with some limitations, but with also some, benefits. For example, per filtering and ongoing filtering is actually very, very efficient there. But OpenSearch baked into industry standard vector search libraries. So FICE, built by Facebook, and NMSlib, which is an Apache licensed open source implementation of one of those optimizations we talked about, so HNSW. And so OpenSearch is geared towards a very efficient, very easy to use vector search. Now, in order to use vector search in OpenSearch, what you need to do, you need to, again, have those vector embeddings, and then you add them to your documents in OpenSearch as a KNN vector field. So you have a new field type that's called KNN vector. You had text, you had integer, Boolean. Now you have also KNN vector. You put that, long list of strings or of numbers, in your document. And now it becomes a vector that is searchable within OpenSearch.
Okay, so it's just like having an extra column on a table in a regular database.
Exactly.
Yeah.
Exactly. But it's indexed in a way, again, given all the engines and all the possibilities and all optimizations, that will let you actually search on that very efficiently. So once you have indexed that, when you define that field in your index mappings, that's what we call the schema of an index in Elasticsearch. You're going to pick the engine to use, or just pick the defaults, right? But you're going to pick the engines to use and the space, right? And then the method or the algorithm. And that's pretty much where you define whether or not you're going to use KNN or ANN, right? So if you're going to go KNN, you probably have a small data set, smallish data set with up to our low number of dimensions. So, for example, the Lucene engine supports up to 10,024 dimensions in a vector. FICE and NMSlib support much higher number of dimensions. And then for some of the approaches, you're actually going to need to pre-train, because if you want to create those groups with centroids like we discussed, you need to basically pre-train. You basically need to tell it, okay, do this clustering, find the centroid for each cluster, and then keep it somewhere. So when I search with ANN, I can actually use it.
And does this happen inside of OpenSearch? Is it like some
Everything
kind of
happens.
create index step and it calculates that for you?
Yeah, everything happens within OpenSearch. So once you created the vector embeddings, that's where the not OpenSearch side of things ends, and when OpenSearch takes full responsibility.
In that case, I think you should give us some guidance on finding the right optimization algorithm.
So on the optimization algorithm itself, you need to test, because it really depends, or it really changes for every use case and every vector space and number of dimensions and all of that. But I can tell you that there are some specific things that you need to consider. For example, if your vector has more than 10,000 dimensions, which is it's quite common to see in pretty much everywhere, then you cannot use the Lucene built-in vector search, at least not for now. There is some sort of an open issue there that they're trying to fix. But for now, it's hard-coded to be 10,000, 10,024. And then you need to use FICE and NMSlib. And that's a significant edge, by the way, OpenSearch has over Elasticsearch, because Elasticsearch does have this limitation. And because OpenSearch has those other engines built in, by the way, they're written in C++, so everything is communicated via JNI. So it's like a lot of integration work has been done to make it work. Then you need to use those engines for higher dimensions. There is a lot of other parameters that are going to be, work differently for you, right? So those engines are going to differ in, for example, accuracy, because again, if you do ANN, then it really depends on the algorithm you're going to use. And while Lucene supports HNSW, which, like we said, it's some sort of it splits the vectors to several layers and kind of tries to figure out which one to use there. IVF, which uses k-means, is supported by FICE and NMSlib, and it's not supported by Lucene. Things like speed of adding new vectors, for example, and the accuracy of doing that. So, for example, like I said, if your data set is static, then you can compile it once and then just run on it. But if you need to continuously add vectors, then it really depends what kind of algorithm you use, because then, once you added a vector, maybe it will not be added to the right group, because that's also be done in approximation. How fast it is to add those vectors. I mean, if you're ingesting thousands of vectors per second, the speed of ingestion is important for you. The memory footprint, that IVF has lower footprint than NHSW because it's pre-compiled. So can you support pre-compilation? So pre-training, right, of that. So there's a lot of things. There is a summary in the OpenSearch documentation that we're showing here. But again, there's a lot of things to consider. There are some options that not shown here. And I do expect that space to grow, no pun intended, to grow significantly over the, 1, 2, 3 years going forward. So essentially, it's still a field that's evolving. And, the advice I'm giving today is probably not going to be the advice I'll be giving in 6 months.
Okay, then let's talk about the last stage of the pipeline, which is where you actually get the results out. How do you do the query? How do you, in practice, do you do the querying?
Sure. So quick reminder, we created vector embeddings. We have now JSON, a lot of JSON documents, JSON formatted documents with those vectors as just, lists of numbers that makes no sense to us human in a file or somewhere. And then we loaded them into an index in OpenSearch using the index mapping definition that we previously showed, right? So we have a vector, KNN vector type field type in the index, and the index has been indexed there. Now we need to search on that. And we also mentioned KNN and ANN. So you want to execute a search on your field, on your vectors, and that search needs to be either exact KNN or approximate KNN. So presumably you've made up your mind which one you're going to use. And then there's two types of queries that you can run. So you're either going to run the brute force approach for basically saying, hey, here are my vectors, just execute that distance metric one by one, sort by that, basically by the distance, and then pick the top K, right? So K being how many results you want back. That would be exact KNN. That would be basically get me the top K similar vectors to the vector I use in the query, right? So there's two ways of doing that. One way would be to use a script score query. They have a lang parameter that basically tells you which language to use, and the language in this case would be KNN. Some sort of a hack, probably. It just sounds like a hack, but essentially it's hey, use a KNN script to sort results, and the script is going to be your vector, essentially, which you pass as a parameter, and that would be running an exact KNN search, which is, again, the brute force approach. Now, with brute force, the brute force approach, the exact KNN, you can use pre-filtering. So if you're going to execute a search that is going to be based on exact KNN, you can pass some sort of a query that's going to filter results for you. So that would be your way of actually executing exact KNN, but hopefully improving performance, because now you don't have to match against or execute the distance metric function against 1 million documents, and you can maybe filter it or reduce it down to 100,000 or 50,000, which would make it obviously much, much, much faster, because you filtered based on, I don't know, some metrics like, I don't know, customer ID or some text in the songs in this case, for example, and so on and so forth, right? So that would actually be a way to optimize that. Another way of doing that is using a painless script. So painless is the scripting language of OpenSearch.
Painless?
Yes, no comment about that. Sometimes it's very painful, but that would be your way. You actually have functions that let you compute things on vectors. So given a vector as a query parameter, you can compare that or find the distance between that vector and the document vector that you're searching on, and compute the cosine similarity, the dot product, and the L2 norm, et cetera, and then return that as the score for the document. So again, it's tomato. It's the same way of doing that, except it provides you some additional value, because you can now take that number and do some, let's say, normalization, some weighting, some additional things with that number before actually using it for the score. So those would be the two approaches of doing KNN search. For ANN search, you have a KNN. This is maybe things start to be a little bit confusing, a KNN query type. So you can run a KNN query type, which this is what we have here, showing here in the slide. And that KNN query type is actually going to execute ANN if you've configured that correctly.
Yeah. Naming things is still hard, right?
Always.
Yeah. Okay. If someone wanted to get in touch with you for some more tailored advice, and that's something you guys do, right?
Yeah, obviously. So like we worked with MyPart, which, by the way, was with a lot of work, a lot of help from AWS through a program called Data Lab in that case. Then, we provide consultancy services, hands-on keyboard services. And that's, again, for search relevance engineering, for implementing vector search, and for cluster optimizations. We also have a product called Pulse, which is some sort of, you can think of it as an automated consultant for OpenSearch, whether the managed service or hosted anywhere. And we can basically connect to your cluster, ingest metrics. We never touch your data. We ask you to block us from access to your data. We only want to ingest metrics. And based on all of those metrics, we can automatically tell you, what are you doing right? What are you doing wrong? What's your cluster posture in terms of performance and security and all of that?
Right.
What avenues of optimizations, and then how much money you are wasting sometimes. So we were able to save customers tens of thousands of dollars per month by just looking at their cluster.
That's cool. And I have to ask, is that rule-based or are you using ML in your cluster optimization software?
Both. So you know this meme where you say ML like you show it for investors and customers, and ML like it's actually implemented, and then you see this manual decision tree and maybe an analyst sitting behind the scenes. So we don't have that, but it's a mixture of some ML, anomaly detection, things like that, and then a lot of our accumulated experience and expertise written in code, essentially.
Cool. Okay. We're going to have to link to that in the notes for this video, along with a lot of other links we've got to gather.
We do have a lot of links, yeah.
Itamar, this is a brave new world, and thank you for navigating us through it.
Absolutely. My pleasure. Thank you, Kris, for hosting this.
Pleasure. That's all we have for you. So it's time to go and brainstorm some use cases. Maybe plan a pilot project. Before you go and do that, if you found this video useful, informative, entertaining, please take a second to click like so that we know. It's always great to get that feedback. And we are planning more episodes. So if you want to catch those when they go live, click subscribe. YouTube will let you know in due course. If you are watching this episode as it goes live, we'll be on hand in the chat if you've got any questions. And if you're not watching it as it goes live, if you're joining us from the future, hello, people of the future, there's the comment box down below, of course. You'll also find our contact details in the video description if you want to get in touch with us directly. And also in the video description, there's all the links that Itamar and I mentioned. Lastly, Matan, Itamar, thank you very much for letting me grill you both. And until next time, thank you for watching.